This session will be on functions and graphs, and we will also be spending some time with coordinate geometry, and then we will try and see how well we can link these two topics there. Suppose you look at a square. I think we all know that a square has an area, and we also know that a square has a perimeter. So every square has an area, and every square has a perimeter, and every circle has a circumference, and in fact you have only one area for a square and only one quantity as circumference for a circle. We all know the formula for area of square as what? Side into side. If you denote S as side, side into side is area. The perimeter is 4 times side. Just look at this carefully. Area, if you denote it as A is S into S. Perimeter, if you denote it as P, so P is 4 into S. We say that area and perimeter are functions of side. Now in general, what happens is, if there are two variables, say x and y, it's quite possible that we can represent one variable in terms of the other. Let's say y and x are two variables, it's quite possible that we can represent y as a relation of x or y as a function of x, which is what we symbolically put it as y equal to f of x. Now here comes what a function is. The typical examples that you come across in mathematics are y equal to x square, or y equal to x minus 1 whole square, y equals x plus 2, y equal to x, y equals 3. These are a couple of examples that you can look at for a function. Okay, the main function you can think of is the polynomial function. In fact, let's start in a deductive way. We give a general form of a polynomial function as y equals x power n, an x power n plus an minus 1 x power n minus 1, and then it goes on up to a naught, where n is a non-negative integer. It's called a polynomial function. In fact, you find these a's, that is the expressions an x power n, an minus 1 x power n minus 1, these are called the terms of the polynomials, and the ai's, that is an minus 1, these are called coefficients of the polynomial. Now if you look at a typical case, say y equals x plus 3, so you find that x and 3 are terms, the coefficient of x is 1. Let's look at another case. So y equals x square plus 3x plus 5. You could see one more example, say y equal to x cube. So we have seen these three things. In fact, we will give a name for these type of polynomials. In fact, we call the first one as linear polynomial because the power of x is 1. So we call it a linear polynomial because line is basically to do with one dimension. Now look at the second case, y equals x square plus dx plus 5, we call it a quadratic or a second degree polynomial. The third case, y equal to x cube, is a cubic polynomial. So we have just prepared a chart like this, wherein polynomials of first few degrees have got some specific names. We call a 0th degree polynomial as constant. Say for example y equal to 4, y equal to 3, these are examples of constant polynomials. In fact, a linear polynomial is something like what we discussed earlier. So out here we got an example of y equals 5x plus 3, and we also have a quadratic case as x square plus 6x plus 5 or 5x plus 6. These type of stuff we call it as quadratic. A cubic polynomial is essentially x cube plus 7x plus 4, what we see here. So we can also go for higher degree polynomials. In general we can talk of nth degree polynomial and all, but we will confine ourselves up to maybe up to 3rd degree polynomial. Then the other type of function that we come across is a rational function. Typically we all know that a rational number is of the form p by q, where p, q are integers. Well, the role played by integers in a rational number is now played by a polynomial in the case of a rational function. Just as we say integer upon integer is a rational number, likewise a polynomial upon a polynomial is what we call it as rational functions. Something like 5x plus 3 by x plus 2, or maybe x square plus 2x plus 7 by x minus 3. These are examples of rational functions. Alright, if a function is given to us, the next thing what we would like to know is how to evaluate this function. That is, how to find the value of a function is what is the next thing that we will discuss. When the functions are defined by a general formula, finding the values of function for a specific values at a specific point is what we term it as evaluation of a polynomial, evaluation of a function. Say for example, we all know the area of square as side into side. That's a general that we can take it as a function. Suppose you want to find the area of a specific square, say of 4 centimeters radius, then what 4 centimeters radius, suppose we want to find the area of a square whose side is 4 centimeters. So what do you do? side into side is the formula. So here, because side is 4, so 4 into 4, 16. We say 16 is how we evaluated this function at the specific point called s is equal to 4. Same way, let us look at this. Suppose you have a polynomial f of x equal to x square plus 2, or a function x square equal f of x equals x square plus 2. You find that let's say we want to find the value at f2 and f3, that is at 2 and 3, what are the values of this function? Yeah, we just have to plug x as 2, so we get 2 square is 4, 4 plus 2 is 6. Likewise, if you want to compute the value of the function at 3, you plug x equal to 3, you get f of 3 as 3 square plus 2 is 9 plus 2 is 11. Yeah, the next thing is we would like to define something called domain and range of a function. So these two words seem to be too mathematical, but they are very simple words to appreciate and understand. Suppose y equal to f of x is a function, the values for which the function can be meaningfully defined is what we call as domain, and the values taken by the function is what is range. Now for example, if you take a square, we know the formula for area of square as side into side. So let us take for example the length of the side is 3. So we say 3 is a part of the domain. When you find 3 into 3, that is 9. So 9 is a part of the range. Or putting it simply, domain is something to do with input, range has got something to do with outputs. However, for any function if you look at, it is not the case that every number can be given as an input. Okay, so we look at domain in a more formal fashion as acceptable inputs or admissible inputs. The set of admissible or acceptable inputs is what we call it as domain, whereas the set of possible outputs of a given function we look at it as range. Or putting it simply, function is a machine for which the inputs are nothing but domain, the outputs are range. That is how we understand and appreciate what is domain and what is range. Let us try and understand this domain. So what is acceptable, what is not acceptable? In case of a machine, we all know by using our common sense we can take a call on what is acceptable and what is not acceptable. Whereas here also, what is acceptable and what is not acceptable for a function, we just have to keep in mind these 3 rules that we are going to make a mention of. The first rule is division by 0 is not admissible. Well, you can't divide a number by 0, that is rule number 1. Rule number 2 is square root exists only for non-negative numbers. First rule is division by 0 is not admissible and square root exists only for non-negative numbers. Suppose you have a function which has a combination of a denominator, that is combination of a rational function and also a component which has got a square root, then what we have to do is we have to make sure that that value which satisfies both the components is what has to be taken into consideration, which is what we formally summarize it as. If a function has multiple terms involving division and square roots, we should go in for the intersection of both the components. Let us understand this in a few examples. Let us take the first case. Suppose you want to find the domain of the function f of x is 1 by x minus 3. So let us recall that division by 0 is not acceptable. Suppose you can evaluate the function at 4. If you plug x as 4, 1 by 4 minus 3 is just 1. Yeah, at 4 no untoward incident takes place. I mean, you can define the function pretty well at 4. Even if you plug x as let us say 0, no harm. You get 1 by 0 minus 3 is negative 1 by 3, no harm. However, if you plug x as 3, you get 1 by 0, that is division by 0 is what is happening, which is not admissible. We say any real number can be taken as an input for this function except 0. So the domain of the function is all real numbers with an exception of 3. Let us look at the second example. Suppose you want to find the domain of this function f of x is square root of x minus 1. We recall that square root exists only for non-negative real numbers. So that means the quantity inside the square root, that is root x minus 1, has got to be a non-negative quantity. When we say non-negative, 0 is also included. That means x minus 1 has to be greater than or equal to 0. That means x can be anywhere from 1 onwards, no stopping, 1 to infinity. The same thing when you put it in interval notation, as we might have seen this in class on inequalities and all, it is 1 to infinity is what is the domain of this function. You can input any number starting from 1 including 1, and from 1 onwards no stopping. So let us look at the third example, this example. Now here you have a combination of this, you have 1 by x minus 3 as well as root x minus 1. As we mentioned that both the components should work. This 1 by x minus 3 would start working for any number except 3, whereas root x minus 1 would work only from 1 onwards. So basically we have to do the intersection of these two. So the intersection of these two is all real numbers from 1 onwards. When you say all real numbers from 1 onwards, 3 is also getting included into that. So all real numbers from 1 onwards with an exception of 3 is what is domain of this function. Let's go for this range. As we already maintained that range is basically the collection of outputs, possible outputs. The first and foremost thing that you got to recall is square of any quantity is non-negative. That is, when you square a number, either you get a positive quantity or 0, but never a negative quantity. There is a very simple way of understanding this. When you say x square, it is x into x. Now if x is positive, we all know that plus times plus is plus. So cool. If x is negative, we also know that negative times negative is positive. Now what else can x be? If x is positive, the product is positive, x square is positive. If x is negative, then x square is positive. Whereas if you plug x as 0, 0 square is 0. So any quantity when you square it is always non-negative. That's the first and foremost thing that you need to know. The second thing that we would like to look at is, in case the quantity is non-zero, when you square it, it's going to be strictly positive. The square of a non-zero quantity is strictly positive. That's another thing that follows from the first point. The second thing, modulus of a quantity. We will be discussing this mod function in a short while from now. Any quantity you take, the modulus of it is always non-negative. So any quantity's modulus is non-negative. Basically modulus is magnitude of a function, magnitude of a number. So that is always non-negative. Apart from these two, let's also look at, if we learn how to plot the graph. If you look at the graph of a function, the heights and depths taken by the function, the heights and depths in the graph determines what is the range. We will apply these three rules in some simple examples. Let's see them one by one. Let's take for instance, you want to find the range of the function f of x is x squared plus 5. The first thing you need to do is, square of a number is non-negative. So when you say square of a number is non-negative, the first term x square is greater than or equal to 0. Now if you add 5 to this inequality, x square greater than or equal to 0, you add 5 on both sides, you get any number greater than or equal to 5. The least value taken by this x square plus 5 is 5. From 5 onwards there is not going to be any stopping. So we put this range as 5 less than or equal to f of x less than infinity, or putting it in interval notation, we could take it as 5 to infinity, 5 is included. Okay, let's take another example. Suppose you are asked to find the range of this function mod x minus 2. F of x is mod x minus 2. As we all know that modulus of x is always greater than or equal to 0, on subtracting 2 on either sides, we get mod x minus 2 as greater than or equal to minus 2, which means this function is going to take all values from minus 2 onwards. So from minus 2 onwards, all real numbers. Now minus 2 less than or equal to f of x less than infinity is what is the range of this function. The same thing when you put across in interval notation, it is negative 2 onwards to infinity, negative 2 being included. Let's take another variety. Suppose f of x is 3 minus mod x. We are asked to find the range of this. Once again we note that mod x is always non-negative. Now when you multiply throughout by negative sign, say if mod x is non-negative, negative of mod x or minus of mod x is going to be less than or equal to 0. We can take it as non-positive. Let me not trouble you with words. It's not going to be positive. So less than or equal to 0. So you have one thing pretty clear, that minus mod x is always less than or equal to 0. Since you have 3, so if you add 3 on both sides, you end up getting what? 3 minus mod x is less than or equal to 3. So the maximum value the minimum value the function can take is 3. So we would put it as this: the range of this function is from negative infinity to 3. So from minus infinity to 3, all real numbers up to 3, including 3, is what is the answer for this question. The range of this function is this. Let's look at another example. Find the range of the function f of x equal to x. Now for the sake of simplicity, we have drawn the graph of it just to highlight that point, how we can understand range from graph's perspective. That's what is seen here. The range would mean, as we saw, that the heights and depths taken by the function in the graph. Now look at this f of x equal to x, it is pretty clear to graph it. So you can see that this graph that is passing through origin, though it is a slanting line, it is able to take all heights. When I say heights, all numbers above the x axis, all levels above the x axis it is able to take, that means it takes all heights, and it is also able to take all depths, that means any value. You can also see that the line is also going into the third quadrant, it goes down further, that means it is also able to take all negative values. When I say negative, anything below the x axis is depth, anything above the x axis is height, and the x axis itself is ground. So all heights, all depths, including the point on x axis is what is being taken. So we say the range of this function is the whole of real numbers.